at in much more detail. Yeah, прошу прощения. Oksana, I don't see the presentation itself on the screen, so please go back. Thank you. So transformer maintenance needs to be looked at in much more depth, even though transformer maintenance is often seen as something that we do sporadically, sometimes done like once a year or once every 6 months or whenever our protocols dictate. Next slide, please. So these inspections, daily inspections, are very important for keeping the transformer in good working condition. This list of preventive inspections in the standard C57.152-2013 is quite extensive. Often what we don't do is we don't check voltages and currents. For example, at one point, overheating of power lines was caused by excessive load due to not knowing these values. Other important things include checking the temperature of the insulating oil and the level of the insulating liquid in the transformer. On a few occasions, we found that transformers and the owners didn't even know what was going on. Sometimes there are even leaks that the owner is not aware of. And transformers usually seem very reliable, and this makes us sure that they will always work correctly. And this makes us neglect these checks, in a manner of speaking. Other things that we can check for are gas pressure, nitrogen pressure, possible leaks. We need to check radiators and general, cleanliness of transformer. On several occasions, weeds or plants were observed in the radiators, which made them very marginally effective at reducing temperatures. Also, radiator connections must be checked for leaks. It's also necessary to do infrared analysis or scanning to see that temperatures at certain points are not entirely out of control. Some of the other things to check are the controls, the wiring, and if the transformer has a breather, then one must ensure that the silica gel in that breather is in good condition. Indications are often ignored or left in poor condition, but they could otherwise give us good and valuable information. We need to check operation of cooling fans. It's important in transformers that are equipped with them. And even check for vermin. At one time during transformer maintenance, a dead animal was found between the gratings. And the body of that animal was about 3 months old. So these are the things that we need to check. If we don't check them, we won't be able to closely monitor the useful lives of the most important asset in our power facilities. And these are only routine checks, but there are things that we must do much more thoroughly. Next slide, please. Next slide, please. Oksana.
I'm sorry, we have technical issues disconnected with the internet on the screen. Just hold on. Can you please keep talking about our topic?
Sure. So, all right. So as we'll see, there is a more or less typical process or configuration for transformer maintenance. What we do first, we analyze the oil, and we also conduct electrical tests. This is usually done at the same time as electrical testing and oil analysis. We do all this simultaneously, and then we're going to inspect the transformer externally. And this alone will give us a lot of information about our situation. What happens is that at this stage, in many cases, we can find weak points and vulnerabilities in our companies or organizations. And the fact is, when analyzing data and taking corrective action, the information we receive is oftentimes ignored. Sometimes people will perform oil analysis, electrical tests, inspect the transformer visually, and know what the conditions are. But when it comes to information, it's just stacked away in some folder, and that information becomes useless. So I recommend, if you are going to use the information and invest in oil analysis then you must analyze the data you collect, because otherwise it's just numbers and they're useless by themselves. And then some corrective action must be taken. Sometimes there have been transformers that after Furan analysis show that they have 15% useful life left, and the owner of the equipment wouldn't even know about it, and they would allow the equipment to continue working without any corrective action whatsoever. And worst of all, they wouldn't even take a forecast for the future life, knowing that the transformer is in rather bad condition. So therefore, it's very important to be able to receive information, but it's actually even more important to know what to do with it and how to analyze it. And if you can go to the next slide. So this was what I was talking about just a minute ago, because of the oil analysis and then the electrical tests and then external inspection. And then the important point is to analyze the data that we receive. And on the basis of that data, we would take corrective action to improve the situation. Okay, next slide now. So now the question comes, when and what exactly tests should we run? It's clear that the transformer has different stages in its lifetime. So the first stage would be commissioning. And this will allow or require us even to run a series of recommended tests. The IEEE C57.152/2013 test standard, tells us that we can have 4 different scenarios. And in these 4 different scenarios, we'll have different recommendations for the tests that we're going to run. There are 4 levels of these possible tests. There are tests, some tests are recommended. Some are performed as needed according to the results of the recommended tests. There are optional tests, depending on the results of the previous ones. And there are those that just don't apply. So for example, infrared thermography will most likely not be applicable to transformers that are being commissioned because this transformer is not energized yet. Or after an external or internal fault has occurred, we don't do that because the transformer is probably still disconnected. So these tests won't matter. But they're very important when the transformer is on and running. So we're going to get the value we want. We now have different tests, and we see that depending on the scenario, we run the recommended test first, then the test that might be required or as needed, and then the optional test. And that leaves us with the tests that do not apply, which we obviously don't do. For example, when there is a problem in the transformer, when our transformer protection trips, one of the most important recommendations is to run the Furan test. And this will tell us the insulation characteristics of the transformer. But in other cases, this test is still optional. Vacuum is a very important thing when commissioning a transformer, but it's not required for maintenance usually, and also unnecessary for external faults. Now that an internal malfunction occurs and we think we're going to repair the transformer, we'll most likely need vacuum purification for this. Next slide, please. And this is another very interesting table that we can find in the SIGRE 445 document, and it's a very well done matrix. We do our oil analysis or our tests many times, but we might not be very clear on what is causing the malfunction and how it's related to the information that we analyze or the information that we're going to get from this particular test. It shows us 3 different problems: overheating, partial discharges, and leakage or seal failures in the transformer. These will be the 3 main groups of transformer problems. Each of them is divided into 3 subcategories. For example, overheating in the core, connections or windings and cooling systems. So if we see that we have a high acidity and we see that overheating has a strong effect on the core, and it will lead to the destruction of the oil and aging of the oil. Now, what the letters H, L, and M stand for is the impact that these issues have. For example, we see that oil leakage has little effect on acidity, while overheating has a strong effect on acidity and interfacial tension. And the strong effect explains to us that oil breakdown and aging can and will occur. Now, for example, partial discharges will have a moderate effect on the breakdown voltage, but high effect on paper. We can learn a lot from this information, and this is a very important analysis tool that tells us that We are usually focused on seeing whether it passes or fails within the limit of the test being performed. Now we have to do the test in the field and see what they tell us. So with this matrix, we can see a lot of information about what the test does, and we can directly relate it to different problems inside the transformer, and we can know the location of the problem much better. And when we have evidence of a problem and know where it is, it's natural to take corrective action. So we already have a method which allows us to link the tests we usually run and connect them to corrective maintenance. Usually, whenever we talk about maintenance of a transformer, we focus on preventive maintenance, which mostly just involves testing. And in many cases, we are good at it, at preventive maintenance, but we don't often, take corrective action. So this presentation is meant to help a little with the corrective processes when we already have a problem and need to do something about it. So as we will see, this type of corrective maintenance is often a step that we do not take. In some cases, there's also a fear of decision making. And as this corrective service usually has something that all companies fear, and that would be the planned shutdowns. And these scheduled shutdowns must be performed after preventive checks give us the indications that we need to correct operation of the transformer. Next, please. I want to be very clear on this. Prior information is always required to perform maintenance. It sounds very strange when someone says that they have to do routine oil filtration every year, or that the oil is regenerated on a date in a calendar. We're going to regenerate the oil on a certain date. Like on this day, we're going to try the transformer because this date has come. That's a bad approach. We must carry out maintenance of transformer based on the information we collect. And even if the information is collected, if research is not done, analysis is not done, and in fact, processes may be performed that are not really needed, or processes are performed on equipment that can no longer be saved sometimes. So this is an important point. So now that we have this information, we can perform various actions, and we'll need to, for example, filter the oil or dry the insulation paper, etc., based on the information we gather. We may need to chemically treat the oil. We may need to add an inhibitor or a passivator, even regenerate the oil. We may need to do mechanical corrections, such as improving the physical connections. It may be that we find leaks in the transformer, problems with gaskets or problems with insulators, etc. And all of these problems must be corrected. And it may be that we find high power consumption, for instance, and maybe that we find high temperatures related to electrical faults or connection points. So all of the things we do, we need to base on the results of our analysis. Next slide, please. On many occasions, corrective maintenance is put aside, and this ends up giving us problems. And the CGRA 445 document presents us with this table, and we're going to work a lot throughout the rest of this presentation based on this table. So the first thing is that once we have done our analysis, we'll be able to see the different elements that are affected within the transformer. For example, we can see a breakdown voltage faults. That is a value that can be decreased. We can see increases in the amount of moisture, and we can see problems in the power factor, dissipation factor, and the interfacial tensions. We can see oxidation of the oil and problems in the power factor, or we can see that the transformer has lost the oxidation inhibitor. Or maybe if we do a little more in-depth analysis, we could determine that the oil has problems with corrosive sulfur and that some additives need to be introduced to prevent the problem from growing, because each of these problems in the oil has different causes, which are now summarized in this table. For example, breakdown voltage can be affected by carbon particles. And one of the causes of carbon particle formation is overheating at some point, or it can be the effect of particles that enter from the outside through leaks, or it may even be caused by tap changers under load, because they can generate particles due to the continuous movement of parts. Therefore, if we have particles, and those particles are the ones that are reducing our breakdown voltage, then we will need oil filtration. And filtration is a very different process from a thermovacuum purification. Now, it may be that the low breakdown voltage problem is due to the water in the oil, and in this case, we're going to need drying, and that would probably involve thermal and vacuum purification, different from filtration. So in this way, based on the information provided by the analysis of the oil, we'll have a different maintenance procedure, and we will know which one to apply. And this leads us directly to our next slide, please. And the later one. Next again. Thank you. So the first thing we need to discuss is filtration. It's really the simplest, the most straightforward process that we have. And it's basically the removal of certain particles with a sieve or a filter of a certain measure, and that allows us to remove or separate particles mechanically. In many cases, we can use synonyms such as sieve, which means removing certain particles that are larger than desired. Hold on just a second. I'm sorry. All right, sorry for this little delay. So this will lead us to the next slide, please. So this will lead us to the ISO oil measurement system. And this system assigns us 3 types of particles. Actually, 3 sizes of particles. There are 4 micron, 6 micron, and 14 micron particles. Now let's see what those ISO codes mean. Those are usually given by 3 numbers. For example, here we have an example of code of 20/17/13. The first number will always refer to the smallest particle, 4 micron particles. The second number will refer to 6 micron particles, which are kind of in between. And the third number will refer to the largest particle, and in this case, it's 14 microns. So now that we have a value of 20, 17, 13, this tells us that we must check this table to determine the minimum values and maximum values. So about 4 micron particles, a code of 20 tells me that I have 5,000 to 10,000 ppm of this particle size. Code 17 tells me that I have 640 to 1,300 ppm of 6 micron particles. And the value of 13 tells us that we have 40 to 80 ppm of 14 micron particles. And that's important because we need to reduce these values to as low as possible so that the codes will show us that our oil is reasonably pure. This is very important when working with oil. And this leads us to the fact that there are actually different types of filters that we'll discuss next. Next slide, please. For example, coalescent filters are capable of removing some moisture. They're not particularly used with transformers since they don't have the necessary absorption rate to reach the levels that we're looking for. Secondly, they're easily depleted or saturated rather, and the cost associated with using such type of filter can run quite high. Other cartridge filters may differ in micron rating, so we can have 90 micron filters or, for example, 0.2 micron filters. These are usually paper filters from different manufacturers, and these filters allow us to remove particles of certain sizes. I would like to note that these filters will usually clog with time and with use, and that will create pressure inside the filtering equipment, so that's something to look out for. It's not recommended, of course, to wash these filters when working with transformers, at least with water, because water is sometimes used to clean these filters, but obviously when using water, it's quite problematic because water can and will contaminate the dielectric oil. So for these types of filters in this application, the best way to clean them is with the same type of dielectric oil that flows in the reverse direction. And obviously the oil that we use to clean the filters should not be reused because it will be saturated with solid particles and it should be safely discarded. Next slide, please. Now, the processing of oil will change depending on what we want to perform. Dehydration is a type of processing that uses other means to remove water. Degassing is another thing that we're going to do to remove gas. And the regeneration or recovery of oil is, well, you can refer to it as microfiltration, in which we have a fineness of about 3 microns. Next slide, please. There is a lot of filtration equipment in the market. For example, these are such simple carts. These are only used to remove particulate matter, and they're ideal for safely recycling oil when we have already processed it, or if we want to move the oil, transfer the oil between 2 containers. And it's very important to do it right to avoid contamination of the oil in the process. And this piece of equipment is very low maintenance and very low cost, and it's very simple. And one thing, sometimes magnets are installed on the filters to remove any metal particles that might be in the oil. Next. Okay, the next process we will talk about is the drying or dehydration process. The first thing we need to talk about is that we need to seal off any incoming source of moisture. You will always see some natural formation or buildup of water in a transformer, but if water increase is not natural, such as caused by oil aging, it's very important to inspect the transformer thoroughly and to check if an abnormal increase in humidity is occurring because of leaks where air with humidity can enter the transformer. So the first thing to do for moisture control is to make sure there is no outside source of moisture in the transformer. Next. The next step is to remove the moisture that we already have in the oil. So in the same SIGRE 445 document, we can see this graph of the effects of combined effects of temperature and moisture on the life of the transformer. So you can see here the blue line, the topmost line, and it shows the dry paper in the transformer. And we can see how temperature affects the life of the transformer. We see that for every 8 degrees of temperature, we lose about half of the useful life of the transformer. So if we, in addition to temperature, also have water, and things become a little more complicated. But let's take the value of 80 degrees. If the moisture content of the paper is 1%, the dashed purple line, the remaining life of the transformer is 30 years. And that's a very good value because transformers are usually rated for 20-25 years of operation. And if we can manage to bring it to 30 years, we get the best performance, actually. In fact, if we can lower the temperatures, we could extend the lifespan of transformer theoretically over 100 years. But if the moisture content of the paper is 3%, so instead of 30 years, the useful life of the transformer is now 6 years with the same temperature. And that's why it's very important to keep moisture out of the equipment. We can do that because it's a variable that we can constantly measure and correct accordingly. So we see that if we increase the humidity a lot, we'll have much more loss, much higher loss of useful life. So you can see that it can drop as low as 4 to 5 years. Once again, it's extremely important to keep humidity inside the transformer low. Next slide, please. Oil dehydration is a relatively straightforward process. It's commonly used with vacuum. We know that the boiling point of water is 100 degrees centigrade at the pressure of 1 atmosphere. So now we can see in this graph that if we're in the Rocky Mountains, for example, at about 10,000 feet of altitude, the boiling temperature of water drops to 90 degrees. This is due to the atmospheric pressure, because at high altitudes, the pressure is lower, and that makes water much easier to evaporate. And this is the principle used in all thermal vacuum processes. It's a tool that allows us to safely extract water from oil. So we can see it in this graph. Next slide, please. We see how the water evaporation curve behaves. And we see that at 153 millimeter mercury, we'll have the boiling point of water at 60 degrees. And we know that after or higher than 65 degrees, oil can be damaged because it loses aromatics. If we lower the pressure in the chamber and the oil has a lot of moisture, or even a small amount of moisture, it's still much easier for us to remove this water from this mixture. So all of these particles, as you can see the blue ones on the screen here, we know from the physics classes that they create forces in all directions equally, including the force that acts on the boundary between oil and a gas. So at this moment, we have the action of these particles as well as the action of the particles that are below in the oil. And because the forces are balanced, it's going to be very difficult for the particles in the oil to break off and exit into the gas phase. But the moment we remove the particles from the gas, there is no more downward pressure exerted on the surface. And so any impact or motion of molecules will cause them to separate from the liquid into the gas phase. And that allows water that's on the surface to be easily detached and absorbed by our vacuum equipment. And that's how we do dehydration and even degassing of oil, because it also works for gas. It's very important to ensure that the higher vacuum we reach, the more water we can extract at lower temperature. And this process is much more efficient on the surface. So we need to maximize the surface area, the contact area between the oil and the gas phase. And there are two ways to do it. There is we can do it laminar, or we can spray the oil. Next slide, please. So based on IEEE standard C57.637, we have our laminar-shaped vacuum tanks in order to have more oil exposure inside the vacuum chambers and to improve the procedure and its results. So here we have elements. You will see the yellow ones. Those are called activator filters. The oil flows across them as it passes through the chamber. And we have, in this vacuum chamber, we have 3 inlets, not 1. So the oil passes over aluminum plates, which greatly increase the surface area of the chamber, and they make the vacuum process a lot more efficient. Next, please. The dehydration process is very similar for all manufacturers and brands, because it's pretty simple. But generally, if you follow the flow of oil from left to right, you'll see that the oil goes into the inlet. It passes through a coarse filter or mesh filter that filters out really large particles. Then it goes to the inlet pump. That pump's usually mounted before, well, for instance, a 25 micron filter. And then oil goes into a heater. It's heated to a temperature about 65 degrees to prevent oil decomposition. And then this hot oil is fed into a vacuum chamber. Back, please. Thank you. So in the heater, the temperature of the oil is increased to, say, 65 degrees, no more than that, because we don't want oil decomposition. And then that oil goes into the vacuum chamber, where pressure is reduced to levels where you can safely heat the oil. So all gaseous pollutants, combustible gases, and water can be extracted from the oil using vacuum at this time. And the vacuum pump discharges all of this extracted material into the environment. So when that is done, discharge pump activates, and that's usually done with the help of level sensors that monitor the level of oil in the vacuum chamber. And it forces the oil through the next filter, which is the polishing or fine filter with much smaller micron rating. And then it goes into the outlet, and the outlet may be connected either to the transformer or it can be connected to an oil container. And this is basically the essence of the dehydration and oil degassing. Next slide, please. Okay. There's another process in the market, and it's molecular filtration. And with this, we can dehydrate the windings. These filters are selective. They use the polarity of water because they effectively absorb water and allow other particles to pass through unobstructed. As we can see here, it's a liquid with some contaminants. Contaminants are red, liquid's blue. And this liquid passes through the molecular filters, molecular sieves, and they absorb some specific particles, and other particles continue to flow through. It's very important because we need to keep chromatographic gases in the oil. We don't need to filter them out. Because if we eliminate those gases, we'll have no way of telling the condition of the oil or deterioration of the transformer. There are filters that can hold up to, say, 9 liters of water that they extract from the oil. And the, excuse me, And the end result, the dryness can be as low as 5 ppm of water in the oil. It's considered quite a low amount of moisture for a transformer. Next, please. This is an example of molecular filtration equipment. It's an inline dryer for the oil. It's connected to the transformer, and it operates continuously. And the rate of flow, the flow rate of oil, and the rate of circulation of oil in this equipment is quite low, but it's compensated by the fact that it dries the oil continuously in cycles. So when it dehydrates the oil, a lot of moisture from the paper will go into the oil to restore the equilibrium, and therefore, in the process of using this thing, the moisture content in insulation paper will also decrease over time. Next slide, please. There is a number of different thermal vacuum units. This is the equipment for degassing and for drying dielectric oil. It can do filtration and degassing, obviously. And this type of machine can have one vacuum stage or two vacuum stages. The two-stage equipment is usually the larger one. As you can see in this slide, the machine on the left has a double-stage vacuum system, and the little card on the right has a one-stage vacuum system. But they basically perform the same function, the same purpose. So two-stage equipment is usually larger, obviously, and the Globecore has equipment with two-stage vacuum systems that has capacities anywhere from 1,000 liters per hour and up. Next slide, please. Okay, another important process is paper dehydration, and these processes are usually much slower. These processes, moisture content in paper has much more serious consequences, and it's something that requires special care. Now, we've all dealt with toilet paper, and we know that wet paper and tissue is much more sensitive to mechanical stress. And this means, although there is always some moisture in the transformer, the paper should still work properly. So in practice, when the transformer paper is dried, the Ferrand parameter is drastically improved, and it's very important to have the right equipment for this purpose. Next. The important thing to consider here is that there are inherent characteristics of oil and paper that influence this, and this is the fact that oil is hydrophobic, which means that it basically hates water, and paper is hydrophilic, which it means it loves water. This means that the oil can and will easily transition from oil to paper. That's why we always hear that 97 or 98% of water in transformer is concentrated in paper, and that's actually true. So the paper drying processes have to be planned in advance, because in many cases it requires to take transformers out of service entirely and send them to the factory or to a specialized workshop for maintenance. Next, please. Another widely used process is creation of vacuum or evacuating a transformer. So when we commission transformer, this process is often used, and what it means is a vacuum pump evacuates the transformer for a certain type, and then we measure the dew point to determine if the transformer is dry enough. Here you have a simple formula that tells us how long it will take for a vacuum machine to evacuate a transformer tank, or actually any space, a closed space, a chamber. This information can be found in the excellent book by Ernesto Gallo. It's called Field Service Manual for Transformers, and I can't recommend that enough. It's a great book. But here we'll see how long, in this formula, we can see how long it takes for us to reach the required vacuum depending on the volume. The volume is V, the rate of the pump, which is S, and the ratio of the initial pressure and the target pressure that we need to reach. Next slide, please. Okay, so now we've seen the drying and vacuuming part, but we want to talk now about oil regeneration. So if we have a problem with power factor or interfacial tension, if we have polar compounds in the oil, because the oil has aged, if we have acids in the oil, which are extremely corrosive to the transformer and the paper, If we have these problems, all of these indicate that oil must be regenerated. And this process is much slower and deeper than the thermal vacuum process. Next, please. There are fairly well-known standards, the IEC 60422-2013 and IEEE C57.637-2015. And they describe the use of Fuller's earth and other processes for oil regeneration. These processes take a long time. Therefore, they're performed on live equipment. So oil is regenerated while the transformer is still online and connected to the grid. The process, like I say, can take a long time because regeneration is akin to microfiltration, and microfiltration tends to take long. Even if we have sorbent columns with 130 kilogram load of sorbent, we'll be able to filter around 100 liters of oil per hour on average. So this is an operation that should be planned ahead so that we ensure uninterrupted operation. Next, please. A definition is that regeneration is a process that recovers oil. It removes contaminants resulting from decomposition, such as polar, acidic, or colloidal liquids, and usually employs absorbents that allow us to regenerate the oil. In this picture, you can see an example of oil before and after regeneration. You can obviously see the improvement in color, which is also a very important indication of quality, as you'll see in the next slide. Next slide, please. Okay, the process usually consists of equipment that can passes the oil through the absorbent. That's pretty straightforward, nothing special to it, right? But what makes it really interesting is that we have equipment that can reactivate the sorbent many times when it becomes saturated with contaminants. The way it's done is we burn the contaminants that are trapped in Fuller's earth. And to prevent environmental pollution from this burning, we also have special filters and catalysts that prevent that. There are different machines. As a rule, what we manufacture ranges anywhere from 2 columns to 24 columns. It can actually be more, and it all depends on client requirements. And this is a rather specialized piece of equipment, but using it will improve the oil in the transformer practically to as good as new condition. Next, please. Okay, so now let's talk about maintenance of oil with additives. The one that comes to mind immediately is an oxidation inhibitor. Next, please. What is it? It's a compound that is used to prevent oxygen from decomposing the oil. Basically, it's a substance that protects the oil. It's an additive that allows us to extend the life of the oil. There are 2 widely known compounds. There's DBSP and there's DBP. And they slow down the rate of oil oxidation, and they're quite effective at what they do. Next, please. In this graph, we can see the effects of what happens, when we don't have oxidation inhibitors. You will see that at a certain point, the oil begins to undergo significant changes. Please take a look at the green curve and the red curve. We can see that we can see the point when interfacial tension, and that's the red line, drops sharply, and neutralization number of acidity of the oil, that's the green line, begins to increase sharply. And it happens quite soon after the inhibitor is completely exhausted. The point of analysis for an oxidation inhibitor is on this blue line, and you will see where it hits 0. So as long as we can determine that it's decreasing, we can add inhibitor and fix it. And basically, it's an indication of sorts. If we determine that the inhibitor is missing a certain expected amount, then we can understand what's going on inside the transformer. Another important thing to note about this image is that a few slides back, you might remember we've seen 2 examples of oil, one before regeneration and after regeneration. And different colors, So you will see that darker oil, in the darker oil, you will already have these processes of interfacial tension reduction and acidity increase, even before, any results, test results will show it. So the color itself is a good indication, okay? Right, next slide, please. The best content for inhibitor, the concentration is somewhere between 0.2 and 0.3%. Anything less than 0.1% is not acceptable. It's very important to understand that this number refers not to volume, but to weight, mass. And also keep in mind, density of oil is 0.87. That tells us that every 100 liters of dielectric oil has an approximate weight of 87 kilograms. So we will need not 300 grams, but only 270 grams of inhibitor for every 100 kilogram of oil. Next, please. Okay, there's another problem that also requires the addition of an inhibitor, or actually a passivator, and that is corrosive sulfur. Corrosive sulfur will damage the insulating paper and copper windings of the transformer, and it's an issue that increasingly affects power transformers now. There are several tests that are carried out in oil to determine the sulfur content inside the transformer. There is IEC 62535 test. It's used to determine to find the copper sulfide residues in transformer paper, known as CCD. ASTM D1275 test is used to determine the effect of silver on copper strips. Power transformers are most susceptible to these problems, as these transformers usually do not have enamel or any cover or shielding on the copper parts. There are various procedures to reduce these degradation processes and slow them down, and one of the most common is the addition of chemicals that create a barrier between the copper and corrosive sulfur. Next, please. The problems arising from corrosive sulfur are irreversible. So once a part of the transformer suffers corrosion damage, it cannot be repaired. But the chemicals that we add usually need to be dosed into the oil with much care, because uncontrolled increase of these chemicals can also be detrimental to the transformer. A good time to add them is when you're doing a thermal vacuum purification, for example, because you can precisely dose the required amount of this chemical into the oil at this point. Ergomet is one of the most widely used chemicals, and is usually diluted in a proportion to produce a concentration of about 100 ppm. It forms a very thin sheet on the copper, which acts as a protective barrier between the copper and the oil. This process of adding chemicals for passivation is continuous, because the concentration of the passivator drops over time, and any value below 25 ppm means that we basically have no protection anymore. Next slide, please. So some of the processes that usually have to be done on transformers are evacuation during commissioning and creating positive pressure in transformers when the transformer is under repairs. And these processes require specialized equipment, such as vacuum units and hot air blowers. And we'll conclude this presentation by showing you some of the globe core equipment that is used for these purposes. Next slide, please. So this is a BV series equipment. It allows one to create vacuum, pool vacuum. It's a two-stage unit. This equipment is equipped with control systems that limit booster pump start to a pressure of 10 millibar only. And it's a very simple piece of equipment, very reliable, very few maintenance items, so very easy to operate. Next slide, please. This is a hot air unit. It's a piece of equipment that allows generation and output of hot, dry air. So when oil is removed from a transformer for repairs, it's obviously the transformer core should be isolated from ambient humidity, because that can obviously be very harmful. This hot air unit generates a very dry airstream, and it keeps moisture out of the transformer. And the recommended dew point for this purpose is about -70 degrees centigrade. So this is what we have, what GlobeCore has for for transformer maintenance. And this concludes our overview of the corrective maintenance processes and the equipment that we offer for such processes, and also the standards that govern analysis and treatment of oil. So I'd like to thank you all for your attention. Once again, if you need to receive a certificate of enrollment or attendance for this presentation, contact your manager at GlobeCore, or contact GlobeCore directly. I'd like to thank you all for attention again, and I hope to see you in the future.